the expression for charge after you solve that function looked like this. We said this was the charging equation. Now, just a couple little things that you should have noticed because we used them yesterday. Q max equals C times V max, where this represents the maximum voltage across the capacitor. We did that substitution to get Q. And I'm writing Q max here to represent the full charge on the capacitor. Now, you were asked to take the derivative with respect to time for the charge. So, I don't know how you decided to do that, but normally I would probably this is how I would do it. I would probably distribute the Q and then take the derivative of each term. I watched somebody do this yesterday. They did it a little different than that. That's fine. But this is how I'm going to do it. So I'm going to take the time rate derivative against Q, which is a constant, minus the time rate derivative against Q e to the minus t over RC. Would you all agree first term is 0? Would you all agree the first term is 0? Yes, this term is 0. Second term is going to be minus Q e to the minus t over RC times minus 1 over RC. Now, you got? That's what I got. Clearly, by how fast you guys are writing, that's not what some of you got. But this is what I got. The left side here, dq dt, is defined as current. This is the time rate of change of the current. Equals minus times minus goes away, and I get Q over RC e to the minus t over RC. Q over RC. Q max over RC. Well, Q over C is voltage. In fact, V max. Right? Voltage of the power supply, most likely. So that means this is V max over R, where that voltage represents the voltage of the power supply. Our capacitor will eventually reach the voltage of the power supply, which means V over R, using Ohm's law, is I max. This will be the maximum amount of current the circuit can sustain. This would be what you would see for current if there was no capacitor at all. So my actual function for the current So now I ask again, for those of you who have the correct answer, which is what I wanted you to do at first, is did what we just witness with the watching the bulb, which is the only thing you can see, did it match this? Well, what is the current at time equals 0? It's not 0, it's I max. That's right. And what is the current after a very long time has passed?
0.
0, right. This is an exponential decay. So the current starts at a maximum, and then over time, the current decays to 0. Now, in order to understand why this didn't maybe meet your expectations, I would like you to find the voltage as a function of time. However, be careful. There's more than one voltage that you need to find. There's going to be voltage as a function of time for the capacitor and voltage as a function of time for the resistor. Could you please find both of those? If you don't know where to start, I will help you. Start here for the capacitor, because the voltage across the capacitor is 100% based on the charge in the capacitor. For the resistor, though, it might not occur to you that voltage equals current times resistance. So allow me to let it occur to you. Let's see, for this one, just divide both sides by C. That would have given you V max times 1 minus e to the minus t over RC. And did you just, for this one, plug in I, multiply by R, and get Vmax equal times e to the minus t over RC? Do you see now why we might have less interesting results than we thought? If you don't, brightness of the bulb isn't just based on current. The brightness of the bulb is the power dissipation of the bulb, which would be voltage times current. The power doesn't change at the same rate as the current does. It changes at a different rate. Both the voltage and the current are diminishing through the bulb. And they do so in equal measure, so even when there's two bulbs there, two bulbs suddenly take a different amount of current and take a different amount of voltage. So our ability to see the time lengthening using the bulbs might not work out the way we'd like. I'm not saying it's always going to be the same. It won't be. That's just because the bulbs have the same resistance. But it's not going to be as interesting because we're not just looking at current. When we're watching the bulbs, we're looking at power. Now, we're going to do this lab tomorrow. When we do the lab tomorrow, you're going to need to construct the circuit. You're going to use not the multitesters, but you're going to use the current and voltage meters, and you're going to measure the rise and discharge time of your circuits. You're going to calculate, in this case, the time variant or the time constant for your circuit. If you look closely, and I'm not sure if you really are, so let me focus your attention onto everything that is part of the charging circuit. So right now, those are the voltages during charging time, and then we have the charge during charging time, and the current during charging time. What should be quite evident is what is controlling the time. That should be quite evident.
The RC controls the time.
It's often called the charging value. Now, I don't generally ever write it like that. I almost always write it as T over RC. But some of the books will write it like this. Some books will write it like this. So it's T over T. I don't do any of these. Okay, 1 over RC is the charging value. You should prove to yourself that the units of resistance times the units of capacitance all cancel out to give you something that's in seconds. You should prove that. The value that has to be up in the exponent has to be a unitless quantity. So RC has to be in seconds. I'm not making that a suggestion. I'm saying tonight you should go home, remember what the units are for an ohm, and remember what the units are for farad, and show that an ohm farad is in seconds. That's not an easy task. That's a heavy lift, because most of you can't tell me what an ohm is, and many of you can't tell me what a farad is. You should prove this tonight. Now, you can't measure the length of time it takes for the circuit to actually reach its steady state condition. By definition, it's infinity. So most circuits, when you're asked about measuring a specific time, they pick something. Like they'll ask, how long does it take to reach 50% of the charge? Or how long does it take to reach 50% of the voltage? That's something you can measure. Now in our circuit tomorrow, we're gonna do a logarithmic curve fit or an exponential curve fit to try and figure out what the RC value is for your circuit. But you're gonna also be able to verify it separately. I'm giving you 1 farad capacitors. You have access to the multi-testers so you can test the resistance of the bulbs. Everybody understand? You're gonna do it for at least 2 different bulb configurations. You'll need to produce the graphs straight out of your phone. You'll connect your phone directly to the meters. You will measure current and voltage at the same time. You'll get one of each meter. So you'll get both the charge and we're about to prove the discharge. All right? That's what our lab's gonna be like tomorrow. It's pretty straightforward. Takes some time for everybody to get all the equipment working right. I have a limited number of capacitors. So our groups are either gonna be kind of big or you're gonna be waiting. I don't know which, I haven't decided yet. But I have, I think, 10 total 1 farad capacitors. I've ordered more, they're just not here. So let's do one more thing, but I think you guys can do this on your own. After I charge the capacitor being fully charged, I disconnected the battery and just discharged the capacitor directly through the bulb. So it was charged to Vmax. Let's say that this side was the positive side and this side was the negative side. I'd like you guys to do the math on proving the discharge relationship for charge, voltage, and current in this circuit. I think you can do it. If it were me and I was trying to provide you with a way to do this, I would consider drawing your loop through that circuit. This object does not maintain a power supply, so it is still a voltage drop. So minus V over the capacitor minus V over the resistor has to equal 0. Going to stop right there and let you guys at your tables with your peoples around you do what we did yesterday. This one's easier, much easier. But you still have to do the whole process. You need to derive a function for Q as a function of T. That's what I want to see. So look at your work from yesterday. You have a set of steps. Give it a try. Again, you'll get there really quick, but you need to be careful. In this circuit, the capacitor starts charged. So at time equals 0, Q equals Q max, not 0. But you should still be copying your work from yesterday. Almost everything is exactly the same.
See?
Okay, so
So then if we go back
we're going to
here,
start by plugging in
right, we
for-
know that when the swing is
Oops.
like this,
what
right,
happened.
we can
Don't do
set
that.
H to be equal
For
to
voltage,
0.
we're going to have, for voltage across the capacitor, we have Q over C. And for the voltage across the resistor, we have I times R. So that's equals 0. The first step is to turn this into a differential equation, which means we have to substitute in a differential. The differential we're going to substitute in is dq dt. So minus Q over C
This, right?
minus dq dt times R equals 0. All right, next step, we need to solve for the differential. So minus Q over C equals dq dt times R. And to get dq dt by itself,
When you ever have this
we'll
situation
say
of doing something else,
dq dt
it's always going to be
equals
the hypotenuse
negative
times
Q over RC.
right?
So now we want to split our differential. So we're going to multiply both sides by dt.
Potential energy is, which is what the work is, right? Because it's going to be that times.
Okay, now we split our differential. I want to collect terms, get everything with T on one side and everything with Q on the other. So,
If that's about forces and this is energy,
so there we go.
right? So this equals
All right, now we want to integrate both sides. So I take the integral on both sides.
right?
The left side, T starts at 0, goes to some time in the future. Q, on the other hand, starts at Q max. Because remember, the capacitor is fully charged. And it goes to some value of Q in the future. A lot of people want to put 0 here because we know we're discharging the capacitor. but we're not trying to find out for perhaps how long it takes to discharge. We're trying to find out a function for the discharge rate. So we're trying to figure out what Q is as a function of time. So we want our top to be our function variables. So left side's pretty easy. Minus 1 over RC can come outside the integral.
So we know the word.
And the integral of dt is just t. And we're going to evaluate that from 0 to t. On the other side, the antiderivative of 1 over q is the natural log of q. And we're going to evaluate that from q max to some q in the future.
I believe.
Right? So plugging in our limits, I get this side negative t over rc. And plugging on this side, I get natural log of q minus natural log of q max.
You can use this.
Now, we're trying to solve this for q because we want q as a function of t. There's a variety of ways to do that, but the simplest I still say is to combine these
See, we found this.
into a single natural log. And then I can get rid of the natural log by raising both to a base of e.
You have it?
And then solve it for q.
Okay. So,
Now,
you know what?
I do understand that this is a lot, but it's a process. So if we were to shrink this down, look at the whole thing, our first step
You didn't do that with kinematics?
from here to here was just Kirchhoff's laws.
Well, the first thing,
And, V equals IR
right?
and
You know how
Q equals CV. That's all we were using.
opposites.
This was creating a differential equation.
And this thing are opposites, right?
And that involved us taking I and substituting in a differential.
Notation is this, f of x,
From
x.
this point to here was splitting the differential.
All this means, but, and then you have
Are you understanding now? Like the way this is
So
Right.
that involved us trying to get something into a form that could be integrated. This was, well, actually, I guess it really goes from here all the way there. This was my
right.
integration.
Same as if I did like f of x.
And then finally, after all done with
If I
integration,
like
algebra.
say I had x.
So when we break it all up, that's what we have. And I know it's a lot, and there's a lot to do, but each piece is worth points. And to be honest, they're going to give the balance of the points to things related to physics, which is going to be here. And this, mostly all math. Now, wouldn't be physics if we didn't at least stop at some point and try and take a look at the meaning of our answer. So let's get back to our circuit and recognize we have Q equals Q max e to the minus t over RC. Notice same time constants. That's good. Obviously, the charge in the capacitor decreases over time. And because we know that, the voltage across the capacitor is Q over C, if I divide both sides of this function by C,
So if I have
I
this,
can rewrite this
right,
as
with nothing inside,
Q over C equals Q max over C e to the minus t over RC.
we can also apply this in reverse. If I see x by itself,
This side
I can do that, right?
has got to be V max, whatever the battery was.
W equals
And this side
f.
must be V as a function of t. So now we have the voltage across the capacitor. Not a problem. But let's be focused on the voltage across the capacitor, not the voltage across the resistor.
Right?
Bring this down here. Take the derivative of Q,
This,
which would be taking the derivative
well,
of this side. Q
just
max
replace with x, right?
e to the minus t over RC. That'll make this, the current as a function of time. So pull the Qmax out, take the derivative of this function, we'll get that function again.
It's called the fundamental theory.
Using the chain rule.
So this is taking an integral. That's what it's called. And what it is,
And
I
now
have a graph.
bring that
Right.
together,
You also have
and we get
correct notation.
Qmax over RC. I get a negative sign and e to the minus t over RC.
Right.
We did this yesterday,
What
but
that means,
Qmax over
we have
C
a
is
graph.
Vmax.
When we're doing this, it means we're finding the area from A to B. So we're trying to find the area of this section.
And then Vmax over R, shouldn't be a surprise. That's going to be the max current.
Right? And what it's basically
Again,
saying
you shouldn't be surprised by this. And the only actual thing that's interesting
is
here
it's breaking
is a
out
negative
into a
sign.
bunch
The
of
current in the
little
system is going to
rectangles,
travel the
right?
opposite
So if I
direction
have-
of what it did while it was charging.
like
Of course it
this,
is.
right?
The capacitor is discharging. So the current's got to travel in the opposite direction for the charges to return to where they
Right,
started.
It's like if I broke it up into a bunch of
So,
pieces
This,
from A to B, right?
this really described most of the surface. All that's left is the voltage across the resistor,
Right? And
which is
that's
just going to be
change,
coming from
right? And the height
taking Ohm's law,
we know is
IR,
of
and substituting my function for I.
right?
So the
So we
voltage
know
across the resistor
That the area
is
of
going to
this
be
is gonna be
negative
f of x
R times I
times
max
dx, right? We can
e
approximate.
to the minus t
Say
over
this is a
RC,
rectangle, right?
or
And then
VR
we
is
add a bunch of these
V
together.
max
And that's
e
gonna
to the
give us
minus
the
t
total.
over RC. It's negative
Right.
to indicate that the voltage across the
But now-
capacitor is in the opposite direction
Right?
of the potential
This is
difference across the
imprecise,
capacitor.
But we know, right, if we make
there
it
we go.
smaller, right, if I have
That's the discharge relationships.